Thank you, the chairperson. First of all, I would like to thank the organizer for inviting me to deliver my talk in this 9th International Conference on Water Resources and Arid Environment. I am Abdul Latif Ahmad from University Science Malaysia. Personally, I feel very honored to be here sharing my research with all the researchers whom I suppose that we have the same common interests, which is related to water and environment. Ladies and gentlemen, Assalamu alaikum and a very good afternoon to all of you. Again, I am Abdul Latif from University Science Malaysia. The title for my presentation is Recycling and Reclamation of Water from Palm Oil Mill Effluent using Integrated Membrane System. I purposely chose this title since I feel this title is very close to the theme of this conference, which is related to water and environment. Ladies and gentlemen, as I share my slide in front of you, you can see my slide, recycling and reclamation of water from palm oil mill effluent using integrated membrane system. First of all, what is the motivation that I chose this title? Because effluent, any effluent, but palm oil is an agriculture effluent. There are a lot of water inside there. That's why it gives me the interest if we can recycle and reclaim those water and at the same time safeguard our environment. Because by reclaiming the water in the effluent, we can reduce the water pollution load to the environment. What I'm going to share within the 20 minutes, because the time is very limited, I will not go in detail of every single detail of the treatment. What I'm going to cover with you is only the skeleton or overall view of the whole process, how the integrated membrane system managed to recycle and reclaim from a very dirty effluent. Ladies and gentlemen, I think all of us aware regarding the water issues across the globe, is about more than 700 million people do not have access to the safe of fresh water. 3.4 million people die from water-related diseases. 2.5 billion people lack of improved sanitation. Droughts impact can be worse in regions with low or improperly managed water resources, resulting in the imbalance between demand and supply. Thus, the topic that I'm choosing is very important and very impactful. If we have the effluent, why not we recycle the water content in the effluent? Of course, we are recycling to the safe level of the recycling. And maybe whatever the finding from my research, whatever the water that we can recycle and reclaim, it is safe for drinking water. I will share with you in a moment. Okay, I would like to introduce with you regarding this worldwide palm oil production. If you look at the bar chart, Indonesia and Malaysia are the champion, are the most producer of the palm oil, But as far as the exporter of the palm oil to the world, Malaysia is still the highest. Even though Indonesia producing the highest, but they also consume quite high because their population is very high. So as far as the export of crude palm oil is concerned, Malaysia cover almost 25% of the production of the exporter of the crude palm oil worldwide. Can I introduce with you as far as the palm oil is concerned, let I shift a little bit on my my video here. Palm oil thrives in the country with tropical climates and evenly distributed rainfall. Palm oil plantation make up 77% of agriculture land in our country. That is huge, you know. More than two-thirds, three-quarters of the agriculture land being occupied by palm oil in Malaysia. And it's about 15% of the total land area of the country. Malaysia palm oil encountered almost 25% or 24.1% to be exact of the total global trade of oil, which is the palm oil and fat in 2018, you know. So looking at these numbers, you know, we can see the importance of palm oil to the country. We can see that how much palm oil been produced, but one have also find out how much effluent been discharged to the environment when we want to produce that huge amount of crude palm oil. Okay, this is some more little background. I will go through very fast because the time is very limited. The lifespan of the palm oil trees is about 25 to 30 years, you know. In every producing year, they can produce between 8 to 12 bunches of fruits. Every bunch load around 10 to 25 kilogram with almost 1,000, between 1,000 to 3,000 fruits. So from this fruit, they press and get the oil. Okay, if you look at this diagram, this is the fruit, the single fruit I'm taking, you know, there is two parts in the fruits. One, we call it endocarp, the inside one, the palm kernel oil, and the outside one is the mesocarp. Basically, the palm oil been pressed in the mesocarp. This mesocarp, the orange in color, you can see it here, full or rich with the oil. Even if you touch the fruit, you can feel the oil in your finger. So while they are processing, they only press that mesocarp and get the extract the oil, you know. And this is the tree, and this is one bunch of the fruits. This one bunch can load up to 25 kilogram, and it can contain the fruits between 1,000 to 3,000 fruitlets. This, what I want to introduce to you, how the palm oil been processed. From the palm tree, they cut the fruits, they bring it to the steam injector. Okay, in this steam injector, they are using a lot of water and steam to sterilize the fruits. That is where they use a lot of water. Until at the end of the day, they process, they press the mesocarp, got the oil, clarifier, you know, bring it here, you know, and after that, they discharge the effluent. We call it POM or palm oil meal effluent. Okay, this is where the effluent is coming from. This is where the water is needed a lot in sterilizing the fruits. Okay. If you look at some photo that I'm taking, you know, nearby the factory, the water, the effluent is very huge. This is one of the photo of the factory that processing or pressing the crude palm oil from the fruits. They are discharging the very, very dirty effluent to the environment. Even though, you know, they have treated it, they are using biological process, but still the water is very, very dirty. I will show you more figures or more photo for you. Okay. All right. This is the fruits. Okay. This is the fruit. In our country, we have more than 300 palm oil mill. You can just imagine. These some of the fruit, the tree look like. It look like a palm, you know. Like if in the Middle East, look like a dates tree because it's category in the palm families. This is from the top view. You can see the tree around the factory. This is the factory. Normally, the factory been developed near to the mill itself, the palm mill itself. You know, so easy to carry the fruit. These are all the fruits. You know, the orange in color. This is the ratio, how much how much effluent been produced? For every single ton of crude palm oil, it requires 5 tons of water, and it discharges 3 tons of effluent to the environment for every single ton of crude palm oil being produced. In our country produced between 17 to 18 million tons of crude palm oil annually. You can just imagine if you multiply by 3, it is almost 53 million tons of effluent being discharged. This is the huge amount of effluent discharged to the environment. Okay, if you look at the characteristic of the effluent, you know, the most important one, what we think that the opportunity that is there is that because the effluent contain almost 95% of water. That is the opportunity. If we can reclaim that water, it can be recycled that water, we can use it back, you know. If this water not been reclaimed, not been recycled, this water will be discharged together with all other impurities in the effluent, and at the same time will affect our environment. So that is the reason why we need to recover this water. The rest is not that so critical. It's only suspended solid and a little bit of oil and grease, you know. The rest is not. That's why the organic matters is very high. The BOD and COD is very high. The rest is only suspended, the fibers, you know. If you look detail on the characteristic of the effluent, you can see BOD and COD is very high, 25,000 and 50,000. The limit that allowed by the environmental agency is only 100. Oil and grease, 4,000 need to be reduced to 50 milligram per liter. Okay, suspended solid from 18,000 to 400. The rest, not that so critical, okay? But what we are interested in is that the water content. This is how the effluent look like. You can see very brown, very smelly. The current technology, if I show with you, this is how they discharge to the open pond, you know. Open pond, they are using the biological treatment. The biological treatment is very slow process to degrade the pollutants. It may take up to 3 months, you know, but there are a lot of disadvantages with the common conventional treatment processes. This some more diagram, I can show you how bad is the effluent. You know, it can build up the area, you know. That's why the pond treatment system, the long ditches like this, open digester tank and closed anaerobic digester tank and land system. This is some of the diagram. You can see how dirty, how thick is the effluent being treated, you know. And when after some time, it build up the area like this, you know. So those are the disadvantages with the conventional treatment system. Solid build up, short circuit of the ponding system, microorganisms sensitive to the changes, emission of the gas, you know, biogas, you know, mostly methane and ethane, long treatment, 3 months, large treatment area, close monitoring, and require a skilled personnel, you know, and it is nuisance to the public because it's smelly. This is the final discharge after treatment. You can see it's still brownish, but this is the one polluting our environment. As I said, the content here, 95 to 96% is water. So now, why not we reclaim, we recycle this water instead of we discharge to the environment? That is the one that gives motivation to us to do this research. I think the principle of wastewater treatment, whether we can reduce the source, which is impossible, we cannot reduce the sources because every single ton of crude palm oil will produce 3 tons of the wastewater, which is the effluent. We cannot reduce the source because unless we reduce the processing amount, we can recycle or we can treat. So the choice is with us. For us, we recycle, we reuse, we reclaim, and at the same time, we treat, you know, so that the amount load to the environment is very, very less. I don't have much time. This whole process of our integrated membrane system, we have chemical and physical treatment, coagulation, flocculation, sedimentation. It passed through the filter press. We want to remove all the, separate the sludge and the supernatant. After that, going through this activated carbon to remove the odors and color. Then this one become the feeder to ultrafiltration. From ultrafiltration, we feed it to the reverse osmosis. From the reverse osmosis, we get the crystal clear water. It meets the standard of drinking water, whether we want to use it as drinking water or we recycle it back to the internal consumption of the mill itself. This is how the process, 6 stages: coagulation, flocculation, filter press, microfiltration, activated carbon, ultrafiltration, and reverse osmosis. I have to rush faster. I show you some of the result. This one just for flocculation and coagulation. We change, we can see the turbidity going down, and after that stability, and also the amount of coagulation and flocculation required also it reach stability. This is only the first part on the physical and chemical treatment. I didn't show every stage result because it requires a long time. As I said, I only show you the overall. The first part, physical and chemical treatment. The second part is the membrane. Okay. This one, turbidity, COD and BOD, you can see a lot of reduction from stage 1 until stage 6. Turbidity, this one referring to the suspended solid, 10,000 becomes 0.81. COD, 26,000 become 314. BOD from 15,000, it become 91. It shows how effective of this system. This is the result of the flux. Basically, the flux, even though it become reducing, but after some time, it almost stabilized. This, the photo of the effluent starting from the very brown here, when it go to the chemical treatment, we get this stage. The third stage, we get this one for the absorption. When it go to the activated carbon, it become the supernatant, become clearer. Go to the ultrafiltration, even clearer. Then go to the reverse osmosis. The water become crystal water, but only by look. But let we analyze the quality of the water, because by look is not guarantee whether the water are good and safe for the drinking. I don't have much time. You look at this quality. The one at the last column of the table, when we compare with US EPA quality, the production of the effluent that we recycle is almost compatible. In conclusion, the water not just safe to be recycled, but the water is safe to be converted to be a drinking water. So we can recover almost 85% of the water content in the effluent. You can imagine how much reduction of the wastewater discharged to the environment. And we can recover the water, reclaim it, and recycle it back to the internal usage of the mill. Okay. So by comparison, a lot of advantages. I don't have much time. I only have 2 more minutes. We have a lot of that. Zero discharge, cost effective. It support the green technology and sustainable development, SDG, sustainable development goal, number 6 and number 14. It is very creative and it's safe environment. We're able to reclaim water complying with the US EPA, when as far as the Malaysian production of crude palm oil, almost 17 to 18, we can recover 85% of the water. At the end of the day, the whole country can recover 45 million tons of water that meet the standard drinking water. You can just imagine. As I said, I cannot go detail. I only cover the skeleton of it, By comparison, normal standard here, the red one, and the advantage of the integrated membrane system and treatment. I also make comparison here. If I compare between the two, membrane and biological conventional treatment, how much advantage of this system, not only recovering the water, but also protecting our environment. It becomes almost zero discharge. Okay, this is the impact to this country and the society. You can see here it meet to the standard. I will not go through. You can read the slide. You can see in whatever written there, because to the interest of the time. With that, you can see the ping here from the palm oil mill. When they are processing the crude palm oil, they are producing palm oil mill effluent. We can recover 85% water here. If we don't want to drink it, that is fine, but at least we can recycle back the water to the internal usage in the mill. With that, with the time that given to me, 20 minutes, I would like to thank again the organizer who are inviting me to give and share my result, to all my postgraduate students, to my university, University Science Malaysia, and to the funder of the research grant, enable us to conduct this very good and very impactful research to secure the water and to sustain our environment to the future. With that, thank you once again to all the audience, and I'm ready to take any question if you have any. Again, thank you very much.
Hello, everyone. My name is Peng Wang. I'm a faculty member at King Abdullah University of Science and Technology, KAUST. First, I would like to thank PSIPW Prize Council for its recognition of my work at Solar Energy Water Nexus. I'm very grateful to be invited to the conference. I feel very much honored to speak to you, along with so many global leaders in water research. So solar energy is abundantly available and is suitable for most of us, if not everyone. Now, one very inspirational fact states that the amount of solar energy our Earth receives within just 1 hour is already more than what is required to power the entire world for 1 full year. Solar energy is clean, solar energy is free. So we should use as much solar energy as possible. Now you may ask me, what do you mean by sustainability at Solar Energy Water Nexus? Well, for me, it embraces two aspects. The first aspect is to use solar energy to produce as much fresh water as possible. The second aspect is to use available water to help produce as much solar energy as possible. Now, in the next 18 minutes or so, I will talk to you about 3 topics. The first one is solar desalination. In this part, I will introduce you the modern and more advanced solar desalination design that is able to produce much more fresh water than conventional solar steel. Now, the second topic is on atmospheric water harvesting. Now, in this part, I will not talk to you about harvesting atmospheric water to produce fresh water. Instead, I will be focusing on harvesting atmospheric water vapor to help PV to cool. Therefore, you can have more electricity from the same PV panel. Now, the last topic is on brine treatment with zero liquid discharge. This process in this context is also driven by solar energy. So the first topic is solar desalination. you may or may not know that the first ever solar steel was invented in the Middle East about 500 years ago by Arab alchemists. Well, from the modern science, modern design point of view, there are two very obvious drawbacks in the conventional solar steel. It has relatively low water evaporation rate. It also has a very low vapor condensation rate. So when those two drawbacks combine, we have the conventional solar steel, as shown in this photo here, not able to give us more than 0.5 liters of fresh water out of 1 square meter of the solar energy absorption area each hour. So many people, including myself, have been working very passionately on how to further enhance both the water evaporation rate and the vapor condensation rate by designing more advanced system for solar desalination. So for the first part, solar vapor evaporation. Now, as we know, for the conventional solar steel, it has the solar evaporation energy efficiency around 25%, right? So in the past 5-6 years, you can see significant progress has been made in solar evaporation energy efficiency. I here just give you a very brief summary of what happened in the past 6 years. Now, starting 2015, you can see here, that's when the new interfacial heating scheme was added to solar desalination process. With this in the system, we could achieve an enhanced energy efficiency around 56%. 1 year later, the design of combined heat barrier and water transport channel further increased the energy efficiency to 33%. In 2007, people realized actually when those two, heat barrier and water transport channel, were separated, we could have better solar evaporation efficiency. In that case, the efficiency could be as high as 87%. In 2018, there are a few three-dimensional structures that were able to deliver an almost perfect solar evaporation energy efficiency, close to 100%. At the same time, efforts have been made to enhance the water vapor condensation performance. In 2018, Professor Arsenari in Italy came up with this nice design of multi-stage membrane desalination. And you can see here in this design, the water vapor condensation latent heat from a previous cycle will be transferred, reused to the next cycle to drive water evaporation there. So you see here, the same amount of heat can be utilized for multiple cycles within this design. Therefore, with this design, you can expect that the water production rate can be significantly enhanced in comparison to the conventional solar steel. However, there is a problem with this design. And you can see here, for this design, the water flow is dead end. So it is not suitable for continuous operation. It is not suitable for practical application. Before showing you some work we did, I want to brief you on the importance and the problem of photovoltaics, or PV. As we all know, PV is arguably the most popular renewable energies these days. Well, PV is not perfect. As a matter of fact, it has a very serious problem, overheating. Why is this? Well, it turns out the commercial PV has solar to electricity conversion efficiency between 10 to 20%, meaning that 80 to 90% of the absorbed solar energy by the PV is not converted to electricity. Instead, it is converted to heat. Therefore, PV panel has a lot of heat, waste heat. That's the reason why PV has an overheating problem. In one of our projects, we found those PV waste heat a purpose. So as you can see in this sketch here, in our design, we creatively use the waste heat of the PV panel to drive multi-stage membrane distillation for seawater desalination. And as you can see here, in this design, the waste heat of PV flows naturally into membrane distillation. And one additional feature of this design is that we have cross-flow mode in our system. Now, having this cross-flow mode is important because it allows the whole system to operate continuously. Therefore, it's suitable for practical application. So we call our system photovoltaic membrane distillation, or PVMD. In 2019, when we first published this concept, the water performance or freshwater production performance by seawater desalination was around 2 LMH, liters out of 1 square meter each hour. Now, this is already much higher than no more than 0.5 LMH for conventional stainless steel. And for the first generation device at that point, the PV panel was able to produce its regular electricity, meaning that it did not produce more, it did not produce less electricity as compared to the PV panel without water production function. I have a good news to share with you, that we have significantly improved both the water and the electricity generation performance of the PVMD in the past 2 years. And you can see from this figure on the bottom left, one of our latest devices is able to produce fresh water at a rate of 4.0 LMH, which double the one we reported in 2019. What is more is that in our latest design, as you can see from the bottom right figure, our system was able to reduce the temperature of the PV panel significantly while producing much higher water production rate. You know, with a lower PV panel temperature, we can expect more electricity being generated by the same PV panel. So to summarize this part, I want to say that there are many benefits associated with PVMD. First, it utilizes solar energy to its full capacity. Secondly, it produces a lot of fresh water and electricity from the same PV panel, and it saved land area requirement. Now, at this point, we are working hard to make our PVMD system to be able to produce zero liquid discharge. So this is still work in progress. Now, moving on to the second topic, atmospheric water harvesting. Now, there is really a lot of water in the air. it is said that the amount of water constantly stored in the atmosphere is about 6 times all water in all of the rivers on Earth. Therefore, getting fresh water from the atmosphere is an interesting idea. However, as I said earlier, I'm not going to talk about this topic today. Instead, I want to talk about how we use atmospheric water to help PV panel to cool, so to get more electricity out of those PV panels. So our design is this. If you have an atmospheric water vapor solvent, you can put this directly on the backside of a commercial PV panel. Now, with this material on the backside of the PV panel, the material will regularly absorb atmospheric water vapor, typically in the evening time and at night when the temperature is low, when the humidity is high. Now, the absorbed water will be stored inside the material as liquid water. So next day, when the sun is up, PV panel is heated up, the heat is transferred to the solvent material on the backside. The material is heated up. The heat will drive the water to evaporate out of the material. Now, we know water evaporation takes a lot of heat out. The same thing happens when we sweat, right? So with this design, as you can expect that the water evaporation during daytime will reduce the temperature of the PV panel. Now, with a PV panel having reduced temperature, then increased electricity production can be rationally expected. Now, to prove this idea, we took one of our materials for atmospheric water vapor harvesting. In this case, it's a hydrogel polymer salt composite. So we stack this on the backside of a commercial PV cell, and then we put the whole thing, outdoors for testing. You see, with the material on the backside of the PV cell or PV panel, in this case, the temperature of the same PV panel was reduced by around 15 degrees Celsius. Our results from field tests in the Kingdom of Saudi Arabia showed us that this design was able to increase the electricity generation by the PV panel by as much as 19%. So this is significant. Those two photos on the right-hand side tells us that our PV cooling design has an option to produce some fresh water. Now, with some precious fresh water coming from dry air, you can think of using those fresh water to help clean up the surface, clean up the dust on the surface of the PV panel. That can further enhance the electricity production by the PV panel. Now, moving on to last topic, solar-driven brine treatment with zero liquid discharge. Now, we know that many industrial processes produce large amount of concentrated brine. Those brine has to be properly treated before discharging into any receiving water body. Zero liquid discharge is always an environmentally attractive option. However, zero liquid discharge is not easy to achieve. Well, we do have technologies available for us to do zero liquid discharge. However, bad news says that those technologies are either very expensive in capital investment or require large land for treating the same amount of brine. So my research has been working on trying to come up with a third option. So we started in 2017 with two-dimensional flat sheet type of solar salt crystallizer. Very quickly, we realized that it will not work because as you can see here, this type of structure has a salt accumulation problem on the surface of light absorptive material. Based on that, we move on to work with three-dimensional, this cup type of three-dimensional solar salt crystallizer. And you can see here, for this design, we were successful in separating light absorbing surface from salt accumulation surface. And we even got very stable, good brine treatment efficiency. However, up to this point, we had been using pure sodium chloride solution as a surrogate for real seawater, under the assumption that pure sodium chloride is a good surrogate of real seawater. Now, if you take a look at this figure on the top right carefully, you will agree with you that assumption was false, because when we use the real seawater or real seawater desalination brine for the same treatment on the same structure, you see the whole system failed within the first 24 hours. So this is to telling us, stop using sodium chloride as a surrogate for real seawater if you are working on desalination, if you're working on brine treatment. Well, this finding really let us struggle for a very long time. Very fortunately, we were able to identify a magic chemical called NTA. With NTA being added to raw brine, raw seawater, you see we were able to achieve a very continuous, effective salt crystallization, achieving zero liquid discharge for those brine treatment at this scale. Now, this is where we are. I always envision that our future with industrial brine should look something like this. 100% of the water is reclaimed, is reused, all of the resources, minerals are recovered. We are not there yet. We have to work hard towards that point. Now, to conclude my talk, I want to stress that the real solutions to our water and energy challenges call for very interdisciplinary research. Therefore, every one of us has to work hard and together to make sure that one day in a near future that everyone in this world will have access to clean water and clean energy. With that, I would like to thank all of you for your time as well as your kind attention. Now I'll be happy to take any questions you may have. Thank you.
Bismillah ar-Rahman ar-Rahim. My name is Mansour Al-Mazrou'i. I am a climate change expert, and I have been working in the King Abdulaziz University for the past 25 years, and have been working in the IPCC Assessment Report 6 as a leading author in Chapter 10 and contributing author in Atlas, as well as of the extremes, which is Chapter 11. I have more than 120 publications and issues related to climate change, mainly over Saudi Arabia. And my presentation today is about climate change in the Kingdom of Saudi Arabia, and I will show it to you in the following slides. So, but before beginning the presentation, I would like to say some facts that climate is changing not only global, but also regionally and locally. And according to WMO, last decade of 2011 up to 2020 was considered as the warmest year in the record. And the signs of climate change is being seen in the warming and cooling of the temperature, as well as increase and decrease in rainfall. And this is related to floods and drought, and also change in the intensity and the frequency of the extremes of the storms. So the warming and cooling, it means that the weather, which is, or the climate, which is going, which is warmer, it's going to be in the future more warming. And the areas where it is cold, it's gonna be more colder. So that is why, and the area which is an increase of rainfall, gonna be more increase of rainfall, and the decrease in rainfall might be getting more decrease in the future. This is just only some signature of the climate change over Saudi Arabia. I'm giving to you an example here of Khulais, where it shows the dead palm trees in Khulais region. This is my village, by the way, which is 100 kilometers northeast of Jeddah. So you can see these palm trees now, this age is more than 80 years, but recently there is a big drought come to the region, and it has shown this drought in the region. And this figure, it shows about Dahran. You can see Dahran, which is, this is the global picture, and this is the Dahran. So you can see the pattern of the increase of temperature globally is also reflected in the Dahran. And this is Bisha. Everybody in Saudi Arabia knew that Bisha is the land of the palm trees. And you can see that the palm trees are getting drier and getting no rain it has in the region. And some of the signature is really the flooding. So this is a case study of extreme rainfall in Jeddah in 25 November 2009. This is one of the most remarkable event and big signature of climate change. And this increase of rainfall has caused the death of more than 120 people. And after 25 November 2009, then there was another event which happened in 26 January 2011, and the rainfall was recorded in the King Abdulaziz University as more than 111 millimeter, and happened in 4 hours. And this is really very significant to a city like Jeddah, which is causing what is called urban flooding in that region, in that city. So this is really very remarkable. And this is an example of Riyadh, where it is caused in 2010, where it was flooded in the city of Riyadh. Definitely not all Riyadh, because Riyadh is really very big. So this is one part of Riyadh, you can see. And one of the significant about climate change of Saudi Arabia, in 2010, temperature was recorded officially of 52 degrees centigrade. That was in 21st of June 2010. So this is really the highest record in Jeddah as 52 degrees. But definitely, I mean, in the northeastern part of the Arabian Peninsula, where in Kuwait, it recorded about 54 recently. And also some of the signature the snow in the north of Saudi Arabia, and this is in Tabuk, by the way. So it is really very rare that you will find snow in Saudi Arabia, but this is another cold event. And another cold event or cold spell of extreme cold event happened in January 2008 in north of Saudi Arabia. You can see Grayat, this is the long spell. You can see it reached up to -9 degrees low. And this is really very big. And many people, in fact, affected in Al-Jawf, in Grayat, and some people died in this cold event. So this is the signal you can see, as I mentioned, that the increase in climate event in the recent decade provides us evidence of the climate change. So what we need to understand the mechanism of climate change is really we need to analyze the climate data and how we can identify the extreme and what is the causes of this extreme. So this is need a lot of effort to do it, in fact. So the case of the extreme event that are happening recently more frequent than before. And we need high resolution climate change models to predict the future changes of these extremes. So we need actually better understanding and in a good time for predicting these extreme events in the future. And also we need to investigate the impact of climate change in the future. So this one is showing what is called in IPCC CMIP 5, which shows the projection of the temperature. And you can see here, according to the period of 2081 up to 2100, how much the temperature will increase in the future. So this one, 0.25, it is going to increase 0.25 degrees, the yellow one. But the red one will increase up to 1.5 or 1.25 degree per in that period. You see the increase is very high. And this region will increase about 2 degrees. And this is the Arabian Peninsula temperature also for using 3 scenarios. This is the new paper, which is published in 2020. So you can read it actually. This is published in the Earth System and Environment. Earth System and Environment. This is a new journal, which is published by King Abdulaziz University and Springfield. So you can see that the scenarios, particularly the higher scenario, is predicting very sharp increase of temperature. And then this is the median scenario, and the yellow shading, the shading part is showing uncertainty, which is now I divided the region into North Arabian Peninsula and South Arabian Peninsula. But both of them, they showed this increase of temperature, although it is more in the North Arabian part, but it also shows this in this regard. And this is the average, model average of CMIP 6, which is also published in the Earth System and Environment. It is published in 2020. And this one also has been included in the IPCC as assessment report 6. So you can see the temperature is really going very high. It may reach more than 5 degrees. This is an ensemble of 31 models. And now this is shows in the assessment report 5 of 2013. And it shows that the temperature, there is a shift in the weather. The northern part of the Arabia, it shows decreasing of rainfall, and the bottom part shows increase. We're gonna explain to you this figure later. So, but I want to go back to my paper, which is published in 2013. This is using CMIP 3, and it shows even the regional model shows increase of rainfall over the southern part and decrease of rainfall in the northern part. And this is really very significant. And when I did another paper, which is going to be published in 2017, it shows with using CMIP5, it shows a similar signal. Increase in the south and also decrease in the north. And this is another one, which is in the air system and environment, which is the paper of the Arabian Peninsula, and it shows that even the CMIP6 shows a similar signal, but also stronger signal. This is in the future. And now here the climate extremes of Saudi Arabia, and you can see that the temperature is going to increase. For example, this figure, that after 2050, it will go temperature very high over the Arabian Peninsula, Saudi Arabia, and it may reach up to 40 and then increase by time. So it is more increase in the temperature. This is the summer maximum temperature in general. You can see number of the days, which is this is the temperature. It goes up to 60 degrees here, you can see. And this is the Riyadh, for example. And this is the projected T maximum temperature, 90 percentile. And it shows really increase, as you can see, as a whole. And it is more over this region. And definitely this is the mountain region, so it is getting less warming. And this one is really a very interesting paper, where it shows that this paper published in 2019, it shows the intensity of the rainfall. For example, if the rainfall in the present climate comes like 80 rainfall, 80 millimeter per day, in the future gonna be more, for example, 130 more, you can see. So this is particularly the north, the eastern part of the Arabian Peninsula. The RCB 8.5 is represented by triangle, and RCB 4.5 is represented by dotted lines. So this is really very clear that in the future is going to be more extreme rainfall, more wet rainfall going to be in the future. And Saudi Arabia is one of the most vulnerable region for the warming of the region, definitely, and it has water resource region in the world. And now here is the models, where applicability of the climate model. When we try to downscale the models, we have to use past and present climate, and then use it for projection. And then there are different RCMs, the regional climate model. One of them is called BRACE, RCM, and COSMO, where we do the validation and make the scenarios, and then do all different types of impact study related to the food, related to forestry, to agriculture, to the environment, to the infrastructure, and also to the water management, for example, and many more, inshallah. Now, the recommendation of my presentation is the following. As I am the lead author of the IPCC assessment report, which is going to be published in 2020, so I recommend downscaling the CMIP6 GCMs by using regional models. And downscaling is required for in-depth understanding of the climate and climatic extreme at local scale. And therefore, there is a need for Saudi Arabia to establish a national climate change center, which I recommend it to be as a priority for the demand of the Kingdom of Saudi Arabia, and to have access to different model ensemble, and also to do different impact studies. And the important thing of the NCCC, which is National Climate Change Center, is going to be devoted to produce high resolution multi-model scenario, and also to assess the uncertainty associated with the climate change projection of the kingdom, and investigate the impact of climate change on different sectors such as water resources, energy, agriculture, health, environment, tourism, and ecosystem. and assist the government formulating policy and strategy to cope with the climate change and esteem to ensure the welfare of its people and sustainable development. Definitely, it will help the government to support its goal for the Paris Agreement. You know, Paris Agreement is trying to impose climate change work for all the countries of the globe. So this one definitely going to support the efforts of Saudi Arabia worldwide. So really we need a national climate change center, and it is really very important for the Kingdom of Saudi Arabia. And this is to coordinate all the efforts of Saudi Arabia and all efforts being done in universities and the other stakeholders, and tackling the climate change and beyond, in fact. And this is the main recommendation, and thank you very much as a whole. Goodbye.
A very good afternoon, fellow colleagues, ladies and gentlemen. I'm Rong Wang from Nanyang Technological University, Singapore. It's my great pleasure to be here today with all of you. I would like to thank the conference organizing committee for the kind invitation. In this presentation, I would like to share with you our work on how to develop the novel hollow fiber membranes for water reuse, from lab study towards commercialization. Basically, my talk will cover 4 parts. In the beginning, I would like to highlight some background information about Singapore's water situation so that you can understand the motivations for us to develop the advanced membrane technology. Then, I will briefly introduce Singapore Membrane Technology Center, where my research was carried out. Next, I will share with you 3 examples to see how we develop the novel membranes for water application from lab study to commercialization. I will wrap up my presentation with a summary. Well, let's start. Here is a world map. You can see Singapore is located at the south tip of Malay Peninsula, just a small dots here. Saudi Arabia is here. Indeed, Singapore is small. The mainland of Singapore measures 50 kilometers from east to west and 34 kilometers from north to south. We only have 5.5 million population. Singapore is surrounded by the sea. We are not only short of the space, we are also short of water. According to the reports from World Resources Institute in 2015, Singapore is ranked top #1 as the world's most water-stressed country. This photo shows water rationing in Singapore in 1960s. We have come a long way to solve the issue of the water scarcity. Today, when you come to Singapore in the downtown, you will see beautiful marina reservoir. We have highest swimming pool in the world that is located at the top roof of this landmark building. Near the Changi Airport, you can see the tallest indoor waterfall. Everywhere you can see the water. I believe you can't imagine why Singapore is a country with severe water scarcity. You may wonder how this miracle happened. Well, with 50 years development, now Singapore has a sustainable water supply system. We have 4 national taps, catchment water from the rainfall, imported water from Malaysia. We also have new water and desalinated water. What is new water? New water is produced from treated used water that is further purified using advanced membrane technology plus UV disinfection, making it ultra clean and safe to drink. In the new water process, You can see two membrane units here. One is microfiltration, another is reverse osmosis membrane process. This photo shows new water looks like. Currently, in Singapore, we have 5 new water plants across the island. New water can meet up 40% national water needs by 2050. New water capacity will be tripled, and that can meet up to 55% of our future water demand. Now let's see desalinated water. We use reverse osmosis membrane technology for seawater desalination. By 2060, desalination will meet up to 30% of Singapore's future water demand. From this data, you can see by 2060, 85% of water supply in Singapore relies on membrane technology. However, under business as usual by 2060, the energy demands for water production will be 4 times of current value. This imposes a big challenge to us. How to develop the highly effective membrane technology? To improve the membrane technologies, there are 2 aspects. One is to develop the highly effective membrane unit itself. Then another part is the membrane engineering process design. Over the years, funding and the resources has been poured into the water research and development in Singapore. We generate a lot of publications, but this is not enough. Another key aspect is the scaling up and the translation of groundbreaking discoveries so they can be put into operational practice. This is a comment from POE, Singapore National Water Agency. It means the laboratory study in the research organization is not sufficient because the TRL level is around 1 to 3. Technology readiness level is pretty low. We need to further push the technology TRL level to the higher and work with industry to commercialize our research. Bear this information in mind. Now I will briefly introduce Singapore Membrane Technology Center, SMTC. SMTC was established in 2008. Professor Tony Finn was the founding director, and I was his deputy at that time. Later, in 2012, I took over as a director, and later I also have my deputy director. SMTC main target is to provide manpower training plus research in membrane science and technology that include IP generation and the technology translation. SMTC big family, including more than 70 full-time researchers and PhD students. We also have over 30 faculty members join the center as a PhD student supervisor or project PI. SMTC has been here for 12 years. Our work covers a wide spectrum from novel membrane development to enhance the module system design, process falling fuel sensor development, and the hybrid system combined with the biological process, novel bioreactor, etc. And this study is for water, environment, energy, and cleaner production applications. We have built world-class laboratories equipped with state-of-the-art instrument facilities to support our research. Now, I'd like to show you 3 examples to see how we develop the novel membranes from the laboratory study and then scale up. First, I will talk about forward osmosis membranes. We know for seawater desalination using membrane technologies, that is reverse osmosis membrane process. We need to apply external hydraulic pressure to push the water flow from the seawater and then we get the clean water. It means external pressure have to overcome the osmotic pressure of the seawater. In contrast, forward osmosis process is a natural process. Water will flow automatically from the low concentration side of the stream to the high concentration side across semi-permeable membranes because of the osmotic pressure difference across the membrane. Forward osmosis membrane process can find many applications. For example, we have produced the water. When we do the dispose, we try to reduce the volume. Then we can use FO process using RO brine, for example, to extract the water across the FO membranes to reduce the volume of produced water. That's one example of FO application. Another application you can see in the food or pharmaceutical process. We can use FO process to concentrate like the protein solution or concentrate the food juice, milk, etc. That's another application. However, back 10 years ago, we cannot find a very good forward osmosis membrane in the market. So we developed the first thin film composite forward osmosis hollow fiber membranes through interfacial polymerization. And we conducted a series of work on this topic. Because of this work, we are very honored to receive the Alternative Water Resources Prize and the Prince Sudan bin Abdulaziz International Prize for Water in 2016. This award is a great recognition that encourages us to continue pursuing membrane innovation for water solutions. So you can see in the past 10 years, we publish a lot in the scientific community, the papers, we generate the patents, and we work with industries to explore different applications. Here, I'm pleased to let you know a spin-off company based on our invention on forward osmosis hollow fiber membranes has been set up in 2018. This company can produce large-scale hollow fiber membrane modules for beverage and the dairy application, for example, to concentrate coffee, tea, milk, etc. Of course, these membranes can be used to handle wastewater to reduce the disposal of the volume of the wastewater. Now, I'd like to talk about the biomimetic membranes. 10 years ago, people are fascinated about the aquaporin water channel protein. People think about, can we incorporate the water channel protein into the synthetic thin film to enhance the synthetic membrane's water permeability? We started this work 10 years ago. You can see the first project supported by the Singapore government was in 2009. Until today, we are still working on this topic. You may wonder, what you have done? Well, in the past 10 years, we assembled a strong team, including biological scientists, for aquaporin protein expression purification. We developed a protocol to incorporate the aquaporin into the synthetic thin film. Then later, we tested for real application. Now we are doing the scale-up of the aquaporin-based biomimetic membrane modules for large-scale application. I quickly give you some examples. This is the early stage work. We incorporate the aquaporin-containing vesicle into the selective layer of the membranes, and we get the flat sheet membrane. Water permeability of this membrane enhanced by 50%. We further improve the formula, incorporate aquaporin into the selective layer of the hollow fiber membranes. Membrane performance, water permeability was doubled, and still maintain high salt rejection. We do the testing using the real feed water from the new water plant, run over 2 years' time. We compare with commercial membrane BW30. Our membranes operate at the same water permeability, like the water flux 20 LMH, but the commercial membranes need to operate at 10 bar pressure. Our membranes only need 5 to 6 bar operating pressure. So these results are very encouraging. So now we're working on the scale up for the biomimetic membranes. We are able to make the 4-inch module, 1 meter long in length. The module contain more than 3,200 pieces of hollow fibers. That's a thin film type, RO type, aquaporin based hollow fiber membranes for water reuse and the desalination. This is the result testing performance. At the same time, we also have a new invention. We identify a type of the biomolecules that can incorporate into the selective layer of the matrix to tailor the selective layer. So we call it bioprogrammable membranes without aquaporin. The key is aquaporin free. And we also quickly scale up. You can see we make the 4-inch module, 1 meter long, and the water permeability is over 6, and the solid rejection over 94-95% of the sodium chloride rejection. Now, these 2 types of the biomimetic membranes has been used for the pilot testing on the local wastewater treatment plant in Singapore. The testing is ongoing. We already test the membranes in pilot scale for 3 months. We will continue run another 3 months, at least a half year, to test our membranes. Now, I will touch about the low pressure nanofiltration membranes. We turn the UF membranes to nanofiltration membranes through interfacial polymerization. And through layer by layer polyelectrolyte deposition to make the membranes have a tightened structure with nanofiltration performance. The uniqueness of our membranes is that it can operate at a low pressure as low as a 2 bar pressure. You may wonder how you can operate the NF membrane at a 2 bar pressure. This is because our NF membranes have a high selectivity. It can reject divalent ions and allow the monovalent ion to pass through the membrane. So osmotic pressure around the 2 sides will be balanced. So we can run the operation at a low pressure of 2 bar. Our NF membranes has also been scaled up to the 4-inch module. You can see the module sample here. We use these membranes in combination with biological process for wastewater treatment. Now, the system is doing the pilot testing in the local Singapore wastewater treatment plant. Because of the NF membranes have a high rejection to the foulants, then the permeate goes through the downstream RO unit can achieve high water recovery as high as 90% recovery compared with the conventional the free water treated by the normal MBR. Normal MBR, when they run to the RO unit, only to get a 75% of water recovery. Okay, time is up. I think I can make a summary here. The growth of membrane technology is assured due to the impending water scarcity. Successful exploitation of next generation membranes is required for improve the membrane process. It is important to improve the technology readiness level for technology cancellation. In SMTC, we have developed novel for osmosis membranes, biomimetic membranes, and the low-pressure nanofiltration membranes. And commercialization of advanced membrane technology should be the ultimate goal of the membrane research, I believe. With this, I would like to thank all the collaborators, research staff, and the PhD students who have worked together with me in the past 12 years. The funding support from Singapore National Research Foundation and QV, Singapore National Water Agency, as well as the Singapore Economic Development Board, who support SMTC, is highly appreciated. I'd like to thank you for your attention. Taking this opportunity, I'd like to say that I'm looking forward to collaboration with any of you if we can find common interests. Thank you. I will be more than happy to take your questions.
Hi, it's my pleasure to share with you our work on scalable solar-driven water production devices. This work that I'm going to talk about is certainly a collaboration with many of my students, as highlighted here, as well as my postdocs, including also collaborators at Shanghai Jiao Tong University. In particular, we've been interested in solar-driven water projection devices for developing compact solutions for arid environments. And the motivation for our work can be very clear as you look at the water scarcity in the world. What you see here is that certainly many parts of the world are experiencing particularly water crises. And there are many parts of the world that in fact have months, actually almost the whole year, by which there is no water available for access. We can also look at the world's mapping in terms of global relative humidity. You can see that in particular that there are certain regions in the world that are quite arid in the climate. And in particular, in a lot of those regions, also there is very limited infrastructure. Fortunately, we can think about also as we overlay the solar energy of the mapping of the global solar energy, that you can see that in many parts of these arid climates, there's quite an abundance of sunlight. And this is where we believe that there is an opportunity for solar-powered water technologies to enable clean drinking water for the world. So I'll start off and share with you some progress that we've made in water harvesting that's powered by sunlight. Now, one of the resources that we have is, in fact, water in the air, and it's equivalent to about 14% of fresh water in lakes on Earth. So there's quite an abundance of water. I think the question is, can we harness that water from the air to create clean drinking water? Certainly, this is not a new concept. Existing water harvesting technologies have existed for some time. When the humidity is relatively high, then in fact, you can use fog harvesting, and that in fact, you can catch the droplets of water onto these various nets to now then create the clean drinking water. However, this only works for very high humidity conditions, essentially near 100%. And the more common one then is known as dewing. So the idea with dewing is that you use a refrigeration system, as was shown here on the bottom, and that when you actually condense below the dew point, so using refrigeration to condense below the dew point, in fact, then you can extract the clean water. Now, you can imagine that in this case, that dewing can be relatively inefficient depending on the humidity and temperature conditions. What I plot here is the efficiency as a function of the relative humidity, and also a function of what the ambient temperature is. You can see that at relatively high humidity conditions, in fact, you can have a reasonable efficiency. However, as you go to lower relative humidities, you get to a point where dewing becomes nearly infeasible. And this is about less than about 40% relative humidity, and that is typical of arid climates. So this poses a challenge for the community in terms of how do we actually extract water from the air when we have low humidity environments. And this is where we've been working for some time, when we started this collaboration with Professor Omar Yagi's group at Berkeley, where we've invented a new approach to harvesting water from air, and particularly targeting the low humidity conditions. The system is shown on your left, and the idea here is we take advantage of a novel material set known as metal organic frameworks. In this case, here's a schematic of the structure. It's a porous material, in fact, a three-dimensional framework that can now absorb water molecules into its surface topography. And so by which we incorporate these MOFs into a layer, we can now capture the water when this material is dry. And then in the sunlight in the daytime, we can now take advantage of the sunlight in the form of heat to now release the water from the porous material and condense it near ambient conditions. So this is an exciting opportunity because now it doesn't rely on refrigeration, as I shared with you earlier, on doing. And that this now relies heavily on the materials choices. So as I mentioned, we were starting off with MOF 801. And the reason for that is shown here. So this I show as a water isotherm. This is looking at the water uptake as a function of the relative humidity. And MOF 801 has really an excellent isotherm to be able to now capture water and release water at low humidity conditions, as highlighted by this isotherm shape. While certainly the uptake is not as high as some of these other metal organic frameworks, however, the humidity, where there's this steep rise in the humidity, is in the conditions for the very arid climates, as I mentioned. So our first prototype we demonstrated in 2007, where you can see here we were able to create a device very much like the schematic, where we integrated the metal organic frameworks into this porous material. And we captured the water at night, and in the daytime, we exposed it to sunlight on the rooftop of MIT and released the water, condensed it onto a thermoelectric cooler, in this case to control the temperature of the condensing surface. And here we can see that clearly from the images, it can in fact get the water droplets from the device. This was a very exciting breakthrough at that time. And certainly you could say, well, where is the actual amount of drinking water? You can see droplets of water, but it's not really significant. And part of it has been related to the material, the amount of material we can incorporate into our prototype at that time. Now, that was also demonstrated at MIT. And what we've done since then is tested it in a more appropriate climate that is arid, such as that in Tempe, Arizona. Here, I want to highlight the temperature as a function of time for a typical day in Phoenix, Sky Harbor. And you can see from here that, in fact, what I wanted to highlight is in these kinds of arid climates, sometimes the dew point can, in fact, be negative. And this, as I mentioned, is a condition by which dew harvesting can be extremely energy intensive, in fact, because you have to freeze water to actually then extract the water. So we wanted to test our device in these kinds of arid climates to help us demonstrate that, in fact, our water harvesting technology, in fact, can work and be effective in these challenging climates. And so what we've shown, in fact, is a modification of a device that we demonstrated earlier. And in fact, we made some modifications to further enhance performance. But the key here is also that instead of using a thermoelectric cooler, now we're using an air-cooled heatsink, which is more representative of the type of device we anticipate. And with this kind of device, we were able to also demonstrate effective water harvesting. Now, I show you a video here, in fact, of the water harvesting behavior as we release the water from the metal organic framework layer. And in fact, you'll see that the viewport fogs up. And as heat is being applied more to the system, you can start to see that the view window now gets rid of the condensed water on that viewport. And again, you can see that there are nice water droplets that form that suggest that this kind of a technology works. Of course, the challenge has been scalability to demonstrate actually a larger quantity of water. And this is where we've been working on for the past couple of years now, is working towards developing water harvesting at larger scales. And that's what I'll show you here in our recent work, in that we've developed a new concept. This is more focused on the actual design of the water harvesting system. And what we've proposed, in fact, instead of using a single layer, as I showed previously, is a multi-stage concept. The idea is having 2 layers of adsorbent for exposed sunlight to the top layer. And in fact, we can now take advantage of the condensation heat and recycle that latent heat of condensation to drive desorption from a subsequent layer. And through this process, we can, in fact, demonstrate increased daily productivity, which is captured by how many liters of water over the area per day, and in fact, also higher efficiencies compared to that of a single stage. Also, in addition to this, because we're using this kind of infrastructure, we needed to now explore other materials that are more scalable. And so we've been looking at zeolites that are commercially available such that we can actually extract a reasonable quantity of water. The material that we're using, as I mentioned, is a zeolite known as Aquazoa ZO1. It's commercially available in large quantities. In addition to that, it has an isotherm, as shown here. And you can see here that it's really good also at reasonably low humidity conditions. We have low regeneration temperatures. And further, what's really critical in the design of these kinds of systems is the material's kinetics in terms of the rates by which we can actually capture and release the water from the material. So we've been able to now characterize material properties, including the isotherm, the crystal size, absorption enthalpy, and the diffusion coefficients, put them into models that help us now optimize device design. And so that's what we'll show you in the results for the next few slides. So here, what I'll show you is the configuration that we've been looking at in terms of our modeling and actually our prototype development. You can see, as I mentioned, it's a 2-layer type device. And what you can see here clearly from our analysis is what I'm plotting here is water harvested liters per meter squared per day as a function of the hot temperature, which is in fact the top layer, where you're exposing the sunlight to the adsorbent. And also on this axis here is efficiency of the device. You can see clearly when comparing a single stage compared to a dual stage, that you have to reach a reasonable amount, a high enough temperature at the top adsorbent layer to, in fact, achieve the desired effect of higher efficiency and a higher amount of water harvested for this kind of dual stage. And so this has been our target in thinking about our design, by which we want to be able to now expose enough sunlight to be able to reach this temperature about 90 to 100 degrees. And this lends itself then to actually getting more water harvested, as well as increasing efficiency of the device. And in fact, we've been able to build this based on understanding of the various aspects of the design. Here is an image of the actual device, what it looks like. You can see that it's significantly larger than our previous prototypes. And by incorporating the zeolites in here, you can see into 4 tiles as we placed onto this copper sheet. You can now integrate it, and also on the back side, we have a finned kind of design for the heat exchange out to the ambient to dissipate the heat, as well as fans to now kind of effectively more move the air out. And this is what the prototype looks like on the rooftop of MIT, as well as we can show the amount of water that we can actually extract from this kind of 2-stage device. And you can see that, in fact, you can extract now a reasonable quantity that it fits into a beaker of about 60 milliliters. We can also look at the temperature as a function of time, and also looking at the solar flux here on to the right. You can see here that the solar flux is a kind of what it looks like over the day. And in fact, if you look at the temperature of the solar absorber, the top absorbent, the bottom absorbent, as well as the top condenser and the bottom condenser and the ambient conditions. One thing to highlight is because of the larger scale device, there is in fact a capacitance of the system that now kind of slows down the response time of the overall device. And that's something to consider as we think about designing these devices. However, when we look at the water harvested as a function of time, In fact, you can see that the results from a kind of a dual stage device are pretty promising. In fact, what you see here, the total is highlighted in blue, and the top layer, the amount of water extracted from the top layer is in red, and the amount extracted from the bottom layer is that in green. And you can see that, in fact, that we've been able to extract about almost 0.8 liters per meter squared per day. That's about twice the productivity of a single stage. And what this suggests is that there is significant promise in this type of approach to design a system by which we have a two-stage as compared to a single-stage type device to enable higher productivity of water as well as a higher efficiency as we think about developing these kind of water harvesting technologies for clean water access. Now, I thought I'd switch gears a little bit and share with you some other work that we've been working on in our lab in developing solar-driven multi-stage solar stills. And it builds on some of the work that I just shared in using a multi-stage type configuration to be able to recycle the latent heat of condensation to drive, in this case, desalination. Certainly, also in often arid climates, there can be salty streams of water, and we can take advantage of small-scale desalination devices that can facilitate the access of this salty water to clean water via evaporation and condensation. And there's been quite a lot of work in recent years to investigate different approaches by which you can try to enhance evaporation and condensation processes and these types of device architectures to achieve higher efficiency. Examples are shown here as development of novel material sets, as well as also novel configurations to now create these highly efficient desalination devices. Certainly, there are still opportunities ahead because the past solar desalination techniques have limitations. The first is that still the water production is relatively low. Because of the limited efficiency still, while there's been interest in pushing this efficiency, there are extra transport resistances due to the closed system, as well as vaporization enthalpy loss to the environment that limits ultimately the efficiency and water production. Also, the second is a limited flexibility of the choice of materials. Often, selective spectral absorbance is needed and a good workability to actually draw the salt water into the device, as well as high thermal insulation. Because of these constraints, often the choices of materials are limited. So what we proposed is a multi-stage configuration we call thermally localized multi-stage desalination. And what we're doing here is we're combining the effect of now vaporizing at the interface via heat and also recycling the vaporization enthalpy via the creation of multiple stages in this device. So the key novelties here then are decoupling the functions of the actual solar absorption, the insulation, and the water transport, by which now we have a single absorber that collects the sunlight, and then the subsequent layers, in fact, don't require the use of expensive absorber. And in fact, we can use pretty low-cost wicks that can now transport the water and evaporate it and condense it to create clean drinking water. And so the second novelty of this, in fact, is enhanced efficiency because of the use of multiple stages by recycling the vaporization enthalpy. And so we've demonstrated this in addition to also doing detailed design efforts. And what we've shown with this thermally localized multi-stage still, here we have a 10 stacked stage device. You can see here, in fact, we're using relatively low cost components. So we have a nylon frame that now on the top where we have the solar absorption happen, we introduce a sheet that's coated with a selective solar absorber that then interfaces with the aerogel, an optically transparent silicate aerogel that allows us to minimize the thermal losses. And meanwhile, we use an evaporative towel, it's essentially just paper towel, to now draw the liquid in from the salt solution and it serves as a wick that then, because of the heat now interfaced first at the absorber layer, it evaporates and it condenses. And on each subsequent layer of condensation, it releases heat, and then you can utilize that heat to evaporate the subsequent stage, and then ultimately get a relatively high efficient device. And the materials costs in this case are low. We estimate that it's about $1.50 per unit. And actually 70% of that comes from the actual nylon frame. So you can imagine as we start to scale that this can be reduced, this cost can be reduced significantly. And so we've taken now this kind of multi-stage device configuration and done some laboratory test experiments under one sun, so about 1,000 watts per meter squared of illumination using a solar simulator. This is a schematic showing how we interface now this multi-stage configuration with a solar simulator, as well as a measurement of the water that we actually create via a scale. And we can look at the temperature of the individual stages. And we can see, of course, as we expect, that a 10-stage mass change should be drastically different than a single stage because of the significant more amount of water that's produced or in this process. And you can see here that the efficiency of a 10-stage device is also much higher than that of a single stage as expected. And also one of insulated 10-stage, of course, is also better. So from these laboratory experiments, we've shown that we can have a steady state production rate of about 5.8 liters per meter squared hour with a thermal efficiency, a solar thermal efficiency of 385%. And we know that the first initial stages, the first three, in fact, contribute to about 45% of the total water production. And the results of this multi-stage using this 10-stage design gives us about a 5-time improvement compared to that of a single stage design. So when we look at the analysis and kind of compare it to what has been done in the past, you can see by being able to now kind of utilize the components we shared, as well as also the multi-stage type design, our efficiencies can be greatly enhanced in addition to the production rates as well. And so this is a really exciting result in thinking about these low cost compact desalination units. Of course, we wanted to also demonstrate this capability out in outdoor conditions, which is more relevant to the realistic situation. And so we placed this device that we've created on the rooftop of MIT again. And you can see the water collection rate as a function of time, as well as from the solar flux from the sunlight. And over this duration, about 5 hours, we were able to collect about 70 milliliters of water with a record high average productivity of about 2.6 liters per kilowatt per hour. So we are very excited about the opportunities ahead with this kind of multi-stage still technology that can enable now another approach to now deliver clean drinking water. So to summarize, we've demonstrated now 2 different approaches, one of which we take advantage of water harvesting from air, as well as desalination using sunlight as a means to now create clean drinking water. We think there's certainly many opportunities ahead. And with that, I'd like to close and thank you all for your attention and also acknowledge all the tremendous funding as well as collaborators we've had to be able to execute, as well as my tremendous students and postdocs that really have done all the work. So thank you very much, and I'm happy to take any questions.
Hello, my name is Dr. Ashok Gadgil. I'm a professor of environmental engineering at UC Berkeley and a faculty senior scientist at Lawrence Berkeley National Lab. I'm going to speak to you today about technology to support human rights to safe water, stop arsenic poisoning. Also give you an update on what I've been doing since my team and I won the IPW prize several years ago. I I start by giving a land acknowledgement that UC Berkeley is located on land that traditionally belonged to Native American tribes, Ohlone tribes, and we all benefit from occupation of those lands and use of those lands, and we recognize the history of the land on which we work. And I gratefully thank for support numerous institutions and donors and advisors and well-wishers and friends of this effort, which has extended for 15 years now. I want to give a little bit of background that there was a successful campaign to switch people from surface water to groundwater, Bangladesh and India in 1980s. And in 1990s, arsenic was discovered in the hand pumps, which led to arsenicosis, and arsenicosis has these horrific effects. The photograph primarily showing ulceration of the hands, including for the child in the lower panel, amputation of fingers and hands, internal cancers, and so on. Access to drinking water is recognized by the UN General as a fundamental human right, and the Sustainable Development Goal number 6 supports clean water and sanitation for all. Even then, hundreds of millions of poor rural people have no other water to drink than groundwater contaminated with arsenic. Arsenic is everywhere, but the problem is most severe in Bangladesh and nearby parts of India. Chronic exposure to arsenic causes numerous horrible side effects or health effects, which are listed in the slide. But we are going to, in the year 2000, WHO called this the largest mass poisoning in the recorded history. Let us now look at only internal cancers and ask the question that if 100,000 people drink water with a given carcinogen over their lifetime, how many excess internal cancers can be expected? And the answer is shown in this graph, where the vertical axis represents excess internal cancers over a lifetime, and the horizontal axis shows different carcinogens which are allowed in water. So the serious one, the most serious one, is ethylene dibromide, which at its MCL over a lifetime causes 12 excess internal cancers. But notice that we exclude in this graph arsenic. What happens if we add arsenic to this graph? Watch the vertical axis now. The excess risk from drinking arsenic-bearing water at its MCL, which is 10 parts per billion, is about 740 compared to all the other risks which are now showing as little blips on the x-axis. That's how bad arsenic is, even at its MCL. But in fact, arsenic concentration tens or hundreds of times higher is detected in water that people routinely drink. And no surprise that people are very, very sick with horrible effects. Here are a number of examples of arsenic removal units or ARUs placed in rural India. And a student of economics was studying how long do they last, how do they function in the world. And they are all based on decent technology that works in the laboratory. This is what happens in the field. 95% of them fail within 1 year. This is a PhD dissertation of Dr. Abhijit Das, who is now a professor of economics. And the reason they fail is not because of the technology by itself, but because the technology was located in the social context without paying attention to financial viability, without social integration, and without sustainability. So this is what we set out to repair, everything that can be integrated in society and can be affordable. That technology is called ECAR. It was designed to fit within a scalable and sustainable technology system. So how does it work? In water, we have these two steel plates and an external battery, which causes one of the steel plates to dissolve in water, which produces Fe2, and then all of arsenic 3 is oxidized to arsenic 5, which then attaches to Fe3 ferric hydroxides. And arsenic also gets removed, but so does phosphates and silicates. They all precipitate down into the water as coagulate. And then we actually get what is called LD, or zero liquid discharge. I want to start with a quote, a famous quote. The best way to have a good idea is to have lots of ideas. So don't be afraid if your idea is going to fail, because you must think that it's worth trying. And if it's worth trying, then it's fine. If it fails, you have more ideas to try. So in 2005, when we started, we didn't know if we'll succeed, but we took a risk. And we were just trying to see if we can remove arsenic. And we could remove arsenic 5 out of pure DI, that's deionized water. By 2010, we had progressed from that little glass beaker on the left-hand side to a big white reactor, 100-liter reactor that you see standing on the ground on the right-hand panel. From there, we went to 600 liters. We went to 600 liters in the field in India, and then to 2,800 liters. We also paid close attention to community engagement and buy-in. In parallel, we pursued 3 tracks: basic science, fundamental science, technology, and reach out to people, and a two-way communication with the community. So not only lecturing them, but listening to them and asking them what do they care about, and answering their questions respectfully and with honoring the fact that they have to live with the technology. And we must respectfully and humbly go there, not as arrogant white-collar scientists being in the village. So this is a process flow schematics, and this is what the huge tanks look like. This is 2015, about a couple of years after we won the PSIPW prize. And the iron plates in the reactor is what is going to dissolve in the water. Here is a team that I'm working with, a small part of the team. Most of them are professors in India. Some of them are staff, research staff in India, and the reactors are in the background. This is how the reactor performs. It has been performing like that for now 5 years, since 2016 beginning until now. Initial arsenic is 252 parts per billion, and final delivered arsenic is less than 3 parts per billion. And here are school children who get water for free in exchange for giving us opportunity to use one of their classrooms to build a plant. But the excess water is sold to thousands of people in the community. That pays for the operation and maintenance and salaries operated by the private sector company, which received all the manuals, documents, and their license. Their name is LivePure. They operate the plant now. So what has happened to the cancer risk? The cancer risk was not 740. Now it has 18,000 if people drank water from the groundwater well. But with the plant operating, there is an 80-fold reduction, and of safe water sells to the community at 1 US cent per liter, meeting and exceeding all WHO and US EPA standards for biological and chemical contaminants of all kinds. It's a financially viable plant. The estimated return on investment is about 30%. The technology approved by the Indian government is 2018. But we have continued to develop the technology for poor rural communities, even in the first world, because they also don't have a right solution. That solution we invented is called air diffusion cathode assisted electrocoagulation, or iron EC, or ASAI. In this case, instead of an iron cathode, we have an air diffusion cathode. As you can see, it allows oxygen to go through a porous wall, and it produces hydrogen peroxide inside. And that makes it 10,000 times faster than the standard e-car that we used in India. And that also makes it compact and produces lots more arsenic-free water at a much smaller volume and therefore much smaller construction cost. We have actually designed this. We have actually built it. We test data. Note that the x-axis is the experiment cycle. We show you 3 experiments each. On the y-axis is a residual arsenic. It shows that if we go fast with e-car, we still get about 600 ppb arsenic. But with ASAI, we get less than 10 ppb arsenic. Another way to put it is what e-car will take 3 hours and 20 seconds to do on the left-hand side panel, duration box. ASAI can do the same, deliver the same quality of arsenic removal in just 30 seconds. So we are funded by the state of California to build and test this system in the rural California community, and that's what we are working on now. It remains a zero liquid discharge technology so that there is no water molecules that are wasted. All the water that comes in shows up in the final finished water stream. That's where I would like to stop. Here is my email address, and at the bottom of the slide is the website of my research group where you can find more information. Thank you very much. It has been a pleasure.
Good evening. My name is Muhammad Abdul Hamid Dawood. I'm a Senior Water Resources Advisor at the Environment Agency Abu Dhabi, and I'm a professor at National Water Research Center, but I'm now on leave from Egypt. I would like first to thank the organizer of the 9th International Conference on Water Resources and Arid Environment in Kinetics, Saudi Arabia. So my presentation today will be about the sustainable management and reuse of treated wastewater in the Arab region. Our region is an arid region, and we don't have a lot of water resources, and the renewable water resources per capita in our region is mostly very negligible, and in some countries it is less than the 1,000 cubic meter, which is the poverty line for water resources. The rainfall is mostly negligible except some in the south of Sudan and some minor frequencies in the northern coast of the Mediterranean Sea or the Red Sea. At present, most of the countries are lying below the poverty line, which is 1,100 cubic meters renewable water resources per capita per year, and except 2 or 3 countries, which is mainly Mauritania, Iraq, and Somalia, but the remaining countries are below, and especially in GCC countries, they are far below. They are less than even 100 cubic meter per capita per day, which is very making the situation is very stressed and under very stressed regarding the availability of renewable water resources in the region. This is also make a lot of it challenging to get the food enough to fill the gap between the existing food and also the importing food from outside the country. So most of the countries are importing food from outside the region, and in some countries the self-sufficient ratio for food is less than 15%. So means that 85% of the food is coming from outside the region. And to produce this food within our region, this means that we have a lot of pressure on the non-renewable resources which we do have, and the resources which we have. At present, all over the world, they started to look after what we call it non-conventional water resources. Non-conventional water resources means the desalinated water or the treated wastewater. Our region actually produced about 2/3 out of the total desalination capacity all over the world. But the desalination is always very expensive, and it needs a lot of energy for production of this fresh water from the seawater or brackish water. Meanwhile, also it has a lot of environmental impact, like the brine water discharge to the Gulf, to the Red Sea. And it needs a lot of caution, and also it is very costly regarding according to the affordability, especially the low-income countries in the Arab region. So most of the region started to look after or to look for using the treated wastewater, which is a little bit cheap, it's available, and it increases with time. At present, the region is producing about something like about 8 billion cubic meter, or even, and recently the statistics recently indicated we are producing about 12 billion cubic meter of treated wastewater. If with this treated wastewater have been treated carefully and the quality have been managed carefully, then this water resources can be used in different uses. Either the agriculture irrigation, the aquifer recharge, or district cooling, or irrigation of landscaping, amenity plantation, a forested area, and many other purposes could be utilize this treated wastewater. In the region, our region now, most of this water, the utilized quantities of this treated wastewater mostly is used for agriculture. Very minor quantities are used for groundwater recharge, but most of this here, as have been indicated here with this gray color, it is discharged to the water courses or to the environment itself. So this is have a lot of environmental impacts, and also it means that we are draining money and draining resources which is not utilized or efficiently utilized or efficiently used. So we have to look forward using these resources as part from the water balance for each country within the region. As I mentioned, at present we are producing about 12 billion cubic meter. About 6 billion are treated, 6 billion are not treated, but only 4.7 are reused. And the remaining, which is about 8 billion cubic meter, are discharged back to the environment with many environmental impacts and challenges. Our expectation, or by the modeling this volumes and the prediction of this volumes, this means that by 2030, the total treated wastewater production will be reaching about 30 billion cubic meter a year. This is a huge amount of water, and if we are not ready to utilize this water, this means that it will be discharged back to the environment or to the water courses. There is, of course, a lot of challenging regarding the reuse of treated wastewater, especially the insufficient investment. It is the lack of financial resources. It is one is very important issue. The cost recovery and the policy coherence. We have also the limited institutional capacity to use this treated wastewater and the policy framework. There is no policy frameworks in most of the country regarding reusing treated wastewater. Also, we are not managing the wastewater and stormwater and from the floods, and the industrial effluent is also sometimes added to the domestic water collection, which add a lot of additional wastes or additional pollution, which is not normally treated even by normal treatment plants. I will give here a very good example from Abu Dhabi Emirate as a case study, which could be followed by other countries or by other states in the region. In Abu Dhabi Emirate, we have three main resources. The first one is the groundwater, which contributes by about 60%, and we have the desalinated water, and we are producing about 1.8 billion cubic meter in UAE in general and Abu Dhabi. And we are using also the treated wastewater. But at present, this is used either for agriculture, domestic, a forested area, amenity plantation, and other purpose. In Abu Dhabi Emirate, we have more than 32 treatment plants. Out of them, we have only 2 are big, but the remaining are small scale treatment plants. But this, we are producing about something like 400 million cubic meter of treated wastewater. Out of them, only 40% is reused, 45% is reused, and the remaining, which is 55%, are discharged back and mainly to South Al Musaffah area in the Arabian Gulf. So it is polluted this area and making a lot of environmental challenges for our marine ecosystem, especially this area is mostly closed system and the water is not circulated, the ambient marine water is not circulated in a proper way, so it makes a lot of environmental challenges for us. Our expectation is that this will be continuously increased by 10%, from 8 to 10%, so it could reach about more than 1 billion cubic meter by 2030. So we started to put a plan to utilize this water. This is the schematic diagram about the production, the collection, and then the treatment, and then the disposal to the environment. And if it's not disposed, some of them are at present utilized. The present utilization in Abu Dhabi Emirates is either for using it for agriculture, for some crops, especially fodder crops, and some also some olive trees, peaches, and some oranges. But most of this water are not used for agriculture. This is I'm speaking here about the 45%. So most of it are used for landscaping, for amenity plantation, for root verges, and not directly for continuous use in agriculture. But there is a plan now to utilize this. Also, we have a very good experiment to advancedly treat this water and reuse it for agriculture in 230 farms. So we are planning now to increase the reuse of treated wastewater in agriculture. So we started to plan for 2 mega projects. We call the first one Dubai Road project. In this, the length of we will pump the water from here, from the end of Abu Dhabi island, with a pipeline of with a length of about 45 kilometers, and this will carry about 140,000 cubic meter a day, and the water will be used for the irrigation of farms and forests. And we have here more than 2,100 farms, which be actually at present they are using desalinated water. So all these farms and this forest along this pipeline and this area is irrigated with desalinated water, which is the 1 cubic meter of desalinated water is costing the government something like 11 dirham, which is more than $2 a day. For each cubic meter. So by using this amount of water, I will save about 140,000 cubic meter of desalinated water, very big cost for the government. The estimate cost for the infrastructure of this pipeline is about 180 million dirham, Emirati dirham, and the construction will be completed by end of 2021. And we will be ready to irrigate 2,100 farms, in addition to some afforested area, landscaping, and amenity plantation along this pipeline. So, and we will save this huge amount of desalinated water daily from the consumption or from the farm use in this area. The second mega project is what we call the Telen Road project, and the water will be pumped from Al-Waspa treatment plants along Al-Ain Road up to Al-Khatma and Al-Khazna, and it will supply about 2,400 farms, in addition to some afforested area and the root verge of Al-Ain root verge along this line. The length of this line is 70 kilometers, and the daily capacity is 250,000 cubic meter a day, and the capital cost is 750 million. All of these farms, all of this afforested area, and here along this pipeline is irrigated with groundwater. And unfortunately, because the groundwater aquifer within this area is non-renewable aquifer system, so we are deteriorating the groundwater, and the groundwater is depleted. The table is falling down here every year by 6 and 7 meters sometimes every year. So we are facing a very big challenges if we continue using only the groundwater. With replacing the groundwater in this area with treated wastewater, this will enhance the situation of the aquifer system in this area, and it will relieve the pressure from continuously using the deteriorated groundwater. And most of these farms, which is more sometimes, as I mentioned, 2,000 400 farms. Most of them are non-operated at present because of the deterioration of the groundwater and the high saline water exists in this area. So by pumping this 250,000 cubic meter of treated wastewater, I am actually replenishing the aquifer, and I am reserving the investment in these farms in this area, and also I am helping to aquifer to recover and to enhance the situation in the future. Also, the volumes between the peak in the summer and winter demand for these farms will be utilized to recharge the aquifer system and to enhance the situation that could be utilized during any emergency. If there is any failure in the pipeline or any problem in the pipeline, the farmers can utilize the groundwater, which is enhanced and recharged by treated wastewater in the future. Within this area, we will save something like about 4,000 groundwater wells, and it will save a huge amounts of operational cost for the owner of these farms. When we speak about this, we have a lot of workshop and sessions and the brainstorm session with the owner of the farm, how they can use the treated wastewater, which irrigation methods they should use, what is the criteria which they should take into consideration, what will be if they would like to use available alternative resources for potable supply and the livestock potable water supply. So we started to have another potable water supply from the network, from the desalination network, and also we will keep one groundwater wells as a backup for any emergency, and we will also advise them how they can carefully select the irrigation technology and the irrigation method to take into consideration any health risk or to protect the soil and the groundwater from the salinity and toxicity hazards. Is agriculture is only used in Abu Dhabi Emirate? And the answer, of course, is no. Agriculture is one of the main demand centers that they can utilize the treated wastewater. But we have another alternatives like the urban use for, as I mentioned, for landscaping, the recreational use. We have many now fountains and artificial lakes, which they use the treated wastewater, and also we have to use it for environmental enhancement. For the groundwater, we are planning to use for the groundwater also, and for industrial use like district cooling, industrial use for outdoor use for landscaping or greening, but not actually in the industrial process itself. And also for potable water use, if we add membrane technology, if we use membrane technology. But our feasibility study indicated that adding membrane technology will add additional cost, and also we will have some brine water discharge back to the environment as a rejected water or brine water produced by the membrane technology. And we will need also additional energy, so it will be costly. So it is better to use the tertiary treated wastewater directly for irrigation, for district cooling, for aquifer recharge or whatever. Before we starting this project, actually this was a proposal to the recharge the whole quantities of water directly to the aquifer recharge. But our detailed visibility and technical study indicating that it will not also technically viable and economically, and it's better to use it directly for irrigation. And if we have additional excess water which is not utilized for irrigation, it could be used for recharging the aquifer. But recharging the whole quantities into the aquifer, it is not the right solution technically and economically. Why? Because the aquifer system here, as you see here, in the coastline, it is most of water is brackish water, and the volume produced near the Abu Dhabi Island or Al Ain, it's actually lie above the aquifer, which is mostly brackish or saline water. So adding additional treated wastewater to this will not enhance the situation. So it's better to use it directly. And if we need to recharge the aquifer outside this region, it will be very costly to build the infrastructure and pumping station to the aquifer, which is suitable for recharge. So we started to build the infrastructure to utilize it directly for irrigation. And if we have excess, we will enhance locally the areas under this farm by recharging the aquifer system within this farm. So visibility wise, we find that it will be better to use it directly for irrigation and not for aquifer recharge. However, if you have excess water, you can use it for enhancing the groundwater aquifers locally. And if you would like to recharge, you need a lot of infrastructure. You have to build the pumping stations, the main transmission pipelines, and then the recharge system, and then the abstraction or the recovery system, the monitoring system. All this will be very costly, and you need also a very comprehensive monitoring to evaluate the recharged water in a three-dimensional, horizontally and vertically, and also the quality of it and how it will interact with the native groundwater within the aquifer system. So these items will add a hell of cost for the end users. Actually, the advantage of using the treated wastewater is a lot. Like exactly you are relying, it is a reliable source of supply, and it is continuously increased with the increasing of the population and increasing of the demand for potable water supply and domestic water supply. It is available near agriculture application because it's produced from the urban areas. It is highly content of nutrients, of course. It is because it is containing huge nutrients like nitrate and phosphorus, which is very good for to enhance the growth of the plantation. We are benefiting from the rural population if we collect the wastewater and treat it and reuse it. We have the experience within the region how we can deal with the treated wastewater, how we can transport it, and how we can utilize it, how we can use it. Actually, also we have the guidelines and the standards, and we carry in Abu Dhabi Emirate a very comprehensive study with FAO, jointly with FAO, to evaluate and to put a monitoring plan for the reuse of treated wastewater in agriculture in Abu Dhabi. Of course, always there will be some necessary consideration and concerns which should be tackled very carefully before going for the use of treated water. The most one is the risk of human health, especially the farmer or the end users that they are dealing with this quality of water or with this type of water at a farm level. The risk on the environment, like if it contains heavy metals or contains any pollutants, which could affect the groundwater or the soil within this area. One of the very important issue in our region is the social acceptance. Social acceptance, we started to solve it in Abu Dhabi by making a lot of brainstorming, a lot of sessions, awareness campaign and sessions for the end users. And we find that there is a lot of acceptance because it is actually a comparison between a fresh water, which is tertiary treated wastewater, with a groundwater, deteriorated groundwater with a salinity of more than 10 to 15,000 ppm, which is it affects their investment, and it has no revenue or no back from this site. So they started to accept it. The end users or the owner of the farm, they started to use it, especially after many sessions, awareness sessions and awareness campaigns, which we started since 5 years back, before even the implementation of this mega project. Also, the cooperation between different sectors. Sometimes there is some competition between different sectors. Should we use it farming? Should we use it for district cooling, for aquifer recharge, or for landscaping and amenity places? So there is some competition. And we should very carefully put the prioritization and who should we use it effectively and efficiently, and which sector is more beneficiary and economically viable more than others, and where will be the return. So we started to make this analysis and the feasibility study. Also, sometimes we need to have required for additional treatment if it's not, but unfortunately in Abu Dhabi, the 32 treatments plants are all of them tertiary treated, level up to tertiary treated. So the quality, according to FAO study and the FAO guidelines and standards, it is suitable for most of crops except some edible crops, which is it's not recommended to use it directly for reusing of treated wastewater. The public health consideration also should be taken into consideration. The design of the wastewater, either transportation, distribution, and also the irrigation system, which you will be used for at the end on the farm, it should be tackled very carefully and it should be designed very carefully. In conclusion, of course, the treated wastewater is considered sometimes, from my point of view, as a renewable resource, part of from our renewable resource, and we have to go ahead and discuss in details how we can utilize it and utilize it. And I gave you an example in Abu Dhabi that by the end of 2021, we will reach zero discharge to environment, and we will utilize 100% of our treated wastewater, and it will add to our water balance in Abu Dhabi Emirates. So it have a lot of environmental sustainability. It could be be help to protect the groundwater. It could be help to as alternative resource for desalinated water and irrigation. So it will help the environment, and it will help also economically to save a lot of money and a lot of energy, which is used for desalination, and also help the environment regarding stopping discharge of this treated wastewater to the environment, either the water courses, the desert dunes, or whatever. So it also have a lot of economic efficiency compared with other alternative resources. For instance, in Abu Dhabi Emirate, we have some water resource valuation, which indicated that the groundwater is costing us between 5 to 7 dirham, which is something like $1.5 per cubic meter, compared with $2 plus for desalinated water, and with less than $1 or about $1 for treated wastewater. So it has some economic efficiency, and it is economically viable to use it. It also can help to contribute to our food security. As I mentioned, most of the countries within our region has a lot of shortage in the water, in the food supply, and the self-sufficiency ratio is very low compared with other regions. So this could help to contribute to the increasing the self-sufficient ratio and minimize the bill of importing food from other size countries. Exporting food from the neighboring countries or within the region. So it will help also the region to contribute to food security issue. With this, I would like to thank you again for listening, and I'm ready for any clarification or questions. Thank you very much, and I will have my details here. You can contact me at any time. Thank you very much.
All right. My name is Kevin Trenberth. I'm a distinguished scholar at the National Center for Atmospheric Research, which is in Boulder, Colorado, but I recently retired from there. It doesn't mean I've stopped working. I'm now working from New Zealand, and the water cycle has been one of my major topics. I have a new book which I've been working on that details a lot of this, what I'll be describing today, along with other subjects relating to climate change. And so on the screen is my opening slide. The changing water cycle is the topic, and it highlights the fact that water is extremely important. It's irreplaceable. It's non-substitutable for many things, and it's more than just another natural resource. And some people say water is life. And so this is another slide which sort of indicates some of the connectivity that occurs, especially between water and climate, and the links with all ecosystems, society. The climate change is on the left, the greenhouse gases, and there are two-way feedbacks in a number of these loops, indicating that also the subject is quite complicated. So one of the main things that my work has involved is how should rainfall and precipitation change as the climate changes? And usually only the total amount is considered, but most of the time it doesn't rain. And so we need to focus also on the frequency and the duration, how often it rains, the intensity and the rate at which when it does rain, the sequence and the duration, the phase, whether it's rain or snow, and I'll illustrate the importance of these in just a second. So, for instance, the intensity and the phase affect how much runs off versus how much soaks into the soils. And so in this example here, I have two stations, Station A and Station B. This is 1 month's worth of rainfall data, and the rainfall amount is the same in each case. But you can see that the distribution and the intensity is very different. In fact, I've designed it here so that the frequency is a factor of 10 different in each case, and so is the intensity, but the total amount is the same. And so what does this mean for the climate at these two different stations? Well, in the first one, there would be drought and wilting plants in the dry period, possibly even wildfires, and then suddenly there's enough rain in 2 days to cause local flooding. At the other station, however, there's never enough rain to produce any runoff. The soil moisture, on the other hand, gets replenished regularly. There's no drought. The plants mostly do reasonably well. And so you can see that the climate in these two places would be quite different. And that illustrates why we need to pay attention to these two things. So the next slide here shows some results of processing of hourly data showing the long-term averages for December, January, February, and June, July, August. And these are fairly familiar. You can see the storm tracks in middle latitudes, the intertropical convergence zone, and the South Pacific convergence zone, the monsoon regions over the continents, and then the movement of those into the northern hemisphere in the northern summer. Those are familiar. So then when we look at the percentage of time that the precipitation occurs, that's what's given in this slide here. And you can see the numbers down here, and I've compared it with the percentage of time that it's fine. And you can see a lot of places, you know, the numbers are somewhere of the order of 10%. But in the major convergence zones and the monsoons, it can easily be 60%, 70%. Well, this is for a threshold which is not much more than a trace. If you go to moderate rain, 0.2 millimeters per hour and 2 millimeters per hour for heavy rain, this is what it looks like. The patterns actually look quite similar, but you can see the numbers are quite different. And so down here for the heavy rains, you're talking about, you know, 1 to 5% for the most part. And but you know, it is notable that the patterns are quite similar. Another way of looking at it is by, instead of looking at daily data, which is often most commonly used and most readily available down the bottom here, we look at 3-hourly data or hourly data. And so in a day when there is some rain, it may only be for 5 minutes, so it would qualify in these other two cases. But it also counts for daily, and the daily frequency is much, much higher. And you can see that we do not get good statistics using daily data. 3-hourly is not that much different than hourly data, but we need to really get down to hourly data in order to properly see what the frequency is and therefore what the intensity is. And so these are the numbers averaged over the globe, the land only and the ocean only, at these 3 different thresholds for, you know, basically not much more than a trace, moderate rains and heavy rains. And you can see for the globe, it's about 11%, but over land where most of us live, it's about 8%, and the ocean is higher. And for the moderate rains, it's about 5%. And so this means that when it rains, it's raining much harder than when the evaporation occurs because that's a continuous process. And a key point about this is whether models simulate these numbers, and most models have trouble getting these numbers right. So one of the implications is that since it only precipitates over 11% of the globe at any time, it demonstrates that the average rate when it rains is 9 times the mean evaporation time rate. You know, 9 times 11 is about 100. Or if you go to the 8%, then 16, something like that. And so the air feed a weather system, a precipitating weather system, 9 times, perhaps maybe 15, 16 times the area, and it comes about through convergence of moisture, not from local evaporation. So a key thing then is that warmer air holds more moisture at a rate of 7% per degree Celsius. This is the Clausius-Clapeyron equation. And it's expressed as a percentage because it's nonlinear. But it also depends on moisture being available. So the relative humidity tends to remain about the same because of the way in which weather systems work, the processes in the atmosphere. And the exceptions are some differences between the land and the ocean, because the moisture comes mainly from the ocean. This is the overall hydrological cycle. And once on warmer land, the relative humidity therefore drops somewhat. And as the land is warming more than the oceans, this means the relative humidity over land tends to go down a little bit, and this has some consequences for some weather systems. And then the moisture availability issue is especially paramount in arid regions. So warmer air holds more moisture. More heat means more drying, more evaporation, and more moisture, which means where it's not raining, things dry out quicker and there's more intense drought. Where it is raining, there's more rain. And so an example that I put together here is if we have a pocket of air that has some water in it, moisture in it, and it rises for one reason or another, whether it's a cold front or a warm front or because it's going over a hill or something like that, then it expands and it cools, and suddenly it rains like crazy. And so heavy rains occur. And so the key thing, and I've illustrated this now with a thunderstorm, is that the moisture that goes into the rain comes from the area around. And I mentioned before numbers like 9 to 16. Take the square root of that. That's 3 to 4. So it's 3 to 4 times the radius of the rainfall area that the moisture is coming into to provide the observed rainfall rates. And that means if there's more moisture in the environment because it's warmer and more is evaporating, it means that it rains harder. And so this is a summary of the overall changes that go on. We have increases in greenhouse gases with climate change. That increases the radiative forcing, as it's called. This is really the global warming, increased heating, if you like. That heating goes into increasing temperature on the one hand, but also increases in evaporation. The increase in temperature increased the water holding capacity of the atmosphere, and the increase in evaporation actually increased the moisture content. And that feeds into all of these kinds of weather systems, all of them. All of them feed available moisture to enhance precipitation rates. It therefore means enhanced latent heat release when the rainfall occurs, and that enhances the storm intensity. It increases the storm intensity. And this applies with things like this big cold outbreak, this Arctic outbreak that occurred over North America recently and produced very cold temperatures in places. But the environment in which that overall storm occurred is got more moisture over the oceans, and there are changes. In some sense, the atmosphere is more unstable, and we get increased intensity as a consequence. So changes in extremes, they really matter for society and human health. And in a warming climate, we get these higher temperatures, heat waves, wildfires, and other consequences, and fewer cold extremes. But in particular, we get more extremes in the water cycle, the hydrological cycle. More intense precipitation, we get longer, more intense dry spells. There's increased risk of flooding and drought, in this case, both extremes of the water cycle. More intense storms, hurricanes, and tornadoes, and this provides major challenges for a water manager. And often the people or the organization that is responsible for protecting us from flooding is quite different than the group that's responsible for providing water for irrigation or for crops. So some examples, this is only since 2017. These are some examples of places where major flooding occurred in India, Bangladesh, Nepal. In the UK, there was major flooding that year. India in 2019, Venice has chronic problems. In Japan, I put this up in particular because in the first part of Japan in July of 2018, there was major flooding, tremendous damage. And then in the same month, they got to over 40 degrees, record-breaking heat waves in the same month, two extremes in the same month. And of course, in California in 2018, it was record-breaking year with all kinds of damage caused by wildfires. And then 2020 broke that record and is now the worst on record. And so there were over 4,200 buildings that were destroyed in the recent wildfires. In the Southern Hemisphere in Australia in 2019-20, there was major bushfires, as they call it there, unlike anything they'd seen before. And it led to very high temperatures and blackouts and tremendous damage to many of the ecosystems and many of the unique animals that Australia has. And we've also seen examples in the Amazon, in the Brazil, in the Pantanal. And so, you know, this is a wetlands area in South America. And so this is occurring everywhere. Now, I thought I'd spend a minute talking about typhoons and hurricanes. They're the same phenomena, but just in different basins. And they depend upon sea temperatures and there's large natural variability. With climate change, we expect more intense hurricanes, bigger hurricanes, longer lasting hurricanes, more flooding rains. And possibly there could be more hurricanes in some cases, although there are reasons why we don't expect that to be in general the case. And so these are examples in 2017 to 2019 in the Atlantic, in the Pacific, and in the Indian Ocean. And you know, the answer to the question at the top of the page is that, well, yes, hurricanes are natural, but they're now supersized. There's more activity than there used to be, and these events would not have occurred in the way in which they did without human-induced climate change. And so they've also been further exacerbated by poor preparedness. People have not prepared adequately, although in some cases, in Southern Asia, in Bangladesh, in Pakistan, in India, evacuation routes and warning systems have been prepared, and there's been tremendous improvements in the loss of life in recent events in that region. So this is the kind of damage that occurs, and often the flooding is extreme, and you know, things break. So this was an example showing that went across the Philippines and then into Vietnam. Just a tremendous number, 8 landfalling hurricanes in Vietnam in 2020. And in the North Atlantic, there were also a very large number of hurricanes, over 30 storms, and we got well into the Greek alphabet. And so there was a lot of attention given to that in the media. Excuse me. In the Southern Hemisphere, in this season, Yasa in Fiji had a major Category 5 storm. It was right over the Fijian Islands at this time. And there was just tremendous damage. Excuse me. And so these extremes matter. They may or may not be rare in some places, but when they occur, they often break records and they produce values outside of previous experience. And so things break. Thresholds are crossed, high impact events, high costs, loss of life and limb occur. And so we need to really worry about these aspects of climate change, their effects on the water cycle. And often, even though the individual effects might be relatively modest, say of the order of 10%, it can be the straw that breaks the camel's back. And so some of the essentials with regard to precipitation are that the understanding of all aspects of it, all of these characteristics I've talked about, is important, and it needs to be replicated in models, and not enough attention has been paid to that. The intermittency is a basic feature of precipitation: the intensity, the frequency, the duration, the amount, the type, the spatial and temporal covariability, if it's raining in one place but not in another, the spatial scales. All of these things are very important. They relate to the extremes, and the dry and wet spells are becoming more extensive and cause major problems for water resources and water resource managers. And so this will be a primary pressure point for society in the future. And so it's a major issue, and I applaud the the current conference for focusing attention on it, and it's a very interesting and important topic. And so this is my contact information. I'll include this slide in the package here. My phone number is in New Zealand, but you can go to my website and find information. And I thought I might close as something to trigger some discussion, mentioning my new book, which should be out about July, August of this year. And it has one chapter which details what is in today's talk. And so this is the topic, and it's at a level intended for advanced policymakers. There's very few or no equations. All the equations, the few equations that are there, are in sidebars. And so you might watch for this. And I thank you very much.